Hi, my name is Jennifer, and today we're going to talk about something that interested me this semester in this class, which was stars. So let's get right into it. The major factors that interest me first from this lecture that we had was that there's 100 billion stars that are in our Milky Way. Out of those 100 billion stars, they also spread throughout a volume space of nearly 100,000 light years across. And then the nearest star to the sun is the Proxima Centauri, which belongs to which is a member of the three-star system Alpha Centauri complex. About 30 stars that are closest to the sun. Out of those 30 stars, there is Sirius, Bernard, Alpha Centauri, and so on. Properties of stars consist of luminosity, temperature, chemical composition, size, and mass. And for us to fully understand those properties, we need to first measure the distance of the stars. Stars' motion is caused by a parallax in spatial motion. Spatial motion has two components, which are radial motion, that it is along the line of sight, and transverse motion, which is perpendicular to the line of sight. And then we're talking about luminosity and apparent brightness, the measurement of the total power radiated by a star. Apparent brightness is how bright the star is seen from Earth. Apparent brightness depends on the absolute brightness, but also on the distance of the star. Apparent luminosity is measured by a magnitude scale. That magnitude scale is related to our perception that we see. It is a logarithmic scale that is also inverted. It is a logarithmic scale because a change of 5 in magnitude changes the apparent brightness to 100. And it is an inverted because the larger magnitudes are dimmer. We can calculate a star's luminosity by knowing its magnitude and distance from the sun. From us. Temperatures. Stars' colors indicate its temperature. Red stars are usually cool and blue ones are hot, which is crazy because in life, if you ask somebody that doesn't know much about stars, if you ask them what they think would be the hottest star, I'm pretty sure they would say red, because everything that we see when it's red, we consider it as hot. But in reality, red is cool when you're talking about stars. And then blue is hot. And we don't see that in life in general. We see completely the opposite, which is crazy. And then stars' radiation is black body radiation. Black body is a theoretical or model body where it observes all radiation that is falling on it. There are 7 stellar spectra categories that correspond to different temperatures. Those 7 categories are much more informative than the black body curves. And on the next slide, I'm going to show you the different levels and categories and all that, and which one's the hottest, the coolest, and all that. So right here is the stellar spectra categories, and I put 2 different graphs so we can see the differences. Well, we can see how we can see it. So over here you have the hottest, which is O, and then we keep on going down, which the red, like I said, that's the coolest one, but we wouldn't be able to see it if we didn't know anything about stars. So over here we have the hottest, which is O, and then it goes down B, A, F, G, K, and M. Those are the categories that we have. And over here the same. Dark blue, it is the hottest, which is O, and then B, and then this is the red is the coolest, which is crazy, I know. Okay, and then stellar sizes. Few stars can be imaged directly by speckle interference. Like one of the stars that can be seen that we can image directly is called Betelgeuse. It is the largest star that can be imaged directly, being 600 times the size of the sun. Crazy. Stars that are unable to be imaged directly, the size must be calculated. We must calculate the size. For us to calculate the size, we need to know the luminosity and the temperature of the star. And then there's different named stars that are giant, dwarfs, and supergiant stars, which is Some of them are right here. This is some of them. And then giant stars have a radii between 10 and 100 times the sun's. Dwarf stars' radii is equal to or less than the sun's. And then supergiant stars, their radii is more than 100 up to 1,000 times the solar radii. Crazy. Then right here, so like I said, right here, some supergiants, giants, dwarfs, all that good stuff. And then we're talking about the HR diagram. The HR diagram shows us like the white dwarfs, the main sequence, the supergiants, and the giants. The HR diagram plots stellar luminosity against surface temperature. When enough stars are plotted, a pattern begins. And then there's 80 closest stars to the Earth that are right here graphed. The main sequence, which is this one, contains the most stars. And then on the white dwarf right here, we have stars that are hot but are not very luminous because of how small they are. So we don't have a lot of those right here, but we have some. But right here, this is why it's on the main sequence, because it holds the majority of the stars. Alright. Next, we are talking about this spectroscopic parallax. We find the distance to a star. We use spectroscopic to find the distance to a star. We don't use parallax. We use spectroscopic to find the distance to a star. For that, we measure the star's apparent magnitude in spectral class. We use the spectral class is used to estimate the luminosity of the star, and then the inverse square law to find the distance. Extends cosmic distance scale to several thousand parsecs. A lot of it changes. And then one thing that I did not mention in my presentation was the stellar masses. Stellar masses determines where a star will be on the main sequence, which we talked about the main sequence right here. So the stellar mass, that helps us know where we're going to put the star when we know the mass. And then most massive stars have the shortest lifetime. So just like the temperature, completely the opposite of what we're used to in life in general. So, and then the small red dwarfs, those are smaller, they have less mass, but they burn their fuel extremely slow and they have a long lifetime. Nothing compared to nothing compared to the massive stars that have a short time. But if anything, stars, there's a lot of information that we can learn from stars, which is pretty cool because, like I said, you see these supergiants, giants, dwarves, a lot of cool stuff that we can learn from this. So like I said, this is why stars was something that caught my attention. I would really look more into it because if there's a million stars out there that we don't even know that existed. It's pretty cool. And a lot of our science in class, in like high school, whatever, we really didn't talk about stars like we do in this class, which this is why I took this class, because it interested me on that, learning about stars. So this is why I chose to talk about this topic, and it was pretty interesting to me and informative. I learned a lot from it. I just didn't put it all into this presentation. But yeah, thank you.